All right, guys, so in this next video, we are going to see that sometimes we might need to use L'Hopital's rule multiple times. So we're going to start off with the problem with e to the x, and we're going to also look at a graph of e to the x and just see some things that we need to know about limits at e to the x. So let's say that I have the limit as x approaches infinity of e to the x over x squared. So when I plug in here, what I get is infinity over infinity, which is indeed one of the forms that allows me to use L'Hopital's rule. But let's just briefly look at a graph of e to the x so that we can see why the limit as x goes to infinity of e to the x is infinity. So if I were to draw a graph of this thing, it's going to look something like this, where e to the 0 is equal to 1. So if I follow this, actually, I'm going to do this in another color so that I can, boom. Okay, so this is what my graph looks like. E to the 0 is equal to 1. Now, if I follow this graph, my x values up towards infinity, I can see that my y values are just getting bigger and bigger forever. So the limit as x approaches infinity of e to the x is just infinity. But if I were to ask you for the limit as x approaches negative infinity of e to the x, it's actually 0. Because if I look at what's happening as I let my x values get smaller and smaller and go down to negative infinity, my y values are just getting closer and closer to the x-axis. They're getting closer and closer to 0. So this limit is equal to 0. And you might see this sometimes looking like the limit as x goes to negative infinity of e to the negative x. So that's also 0. That's the same thing. And then, as we said, the limit as x goes to 0 of e to the x. Well, that's just e to the 0, which is equal to 1. That's defined, so we can just do our limit that way. So that is e to the x, and these are some limits that you should be comfortable with that might be hard to do just with a calculator or what you've learned in the past. You need to know that limit as x goes to infinity of e to the x is infinity, and negative infinity gives 0. All right, so here we got infinity over infinity, so we're going to apply L'Hopital's rule. Let's not forget to write our HR on top. So then I get the limit as x approaches infinity of e to the x over 2x. Now when I plug in again, I get infinity over infinity again. In order to do that, that means I'm allowed to use L'Hopital's rule. So to figure out what this is, I'm actually going to use L'Hopital's rule one more time. So I'm going to have the limit as x goes to infinity of e to the x over 2. And now when I plug in, I get infinity over 2, which is just infinity. So my final answer here is just infinity. And I used L'Hopital's rule 2 times to get it. So it turns out I can use L'Hopital's rule as many times as I want. I can do it over and over and over again, as long as plugging in still results in infinity over infinity or 0 over 0. So L'Hopital's rule can be used over and over again as long as you keep getting infinity over infinity or 0 over 0. The thing is, though, that just because you can use it again doesn't mean that's always the best plan. So every time we have applied L'Hopital's rule, before we even think about doing it again, we should always simplify. So I actually want to bring us up to this previous problem that we did right here, that ln of cosine x with secant x on top. Notice how I didn't even plug in again before I simplified up here. I said negative sine over cosine is tangent, so I can actually cancel those out. Plugging in again would have actually resulted in infinity over infinity again. But using L'Hopital's rule again would not have been helpful. Simplifying first allowed us to just immediately have the answer. So here we're going to say, however, you should always simplify after every application of L'Hopital's rule. Application of HR before applying it again. All right, so we'll just put some little stars here. This is like a key concept, that idea of simplification. Okay, so let's do another problem where we actually have to do some simplification. All right, so let's say that I have the limit as x approaches infinity of ln x over the cubed root of x. Well, when I plug in, I get infinity over infinity. Remember, we looked at the graph of ln before, and we saw that as x is approaching infinity, ln x is also approaching infinity, which means that I can use L'Hopital's rule here. So we'll put our little HR on top of the equal sign, and we'll get the limit as x approaches infinity of 1 over x. And then this right here is like x to the 1/3. So I'm just applying my power rule, 1/3 x to the negative 2/3. Now if I plug in again right now, before simplifying, actually let's do that derivative real quick just to make sure you guys got it. So the cubed root of x prime is equal to x to the 1/3 prime, which is 1/3 x to the negative 2/3. Which I just want to point out is the same thing as 1 over 3 x to the positive 2/3. So I can bring it down because that power is negative. So that said, when I plug in here, I have 1 over infinity, which we reminded ourselves at the beginning was just 0. And then infinity to the negative 2/3 is also 0. So it's like I have infinity to the negative 2/3, but that's the same thing as 1 over infinity to the positive 2/3. So that also just gives me a 0 on the bottom. So in other words, an important thing to pay attention to is that infinity to a negative power is always 0. Infinity to a negative power is always 0. Okay, so I could use L'Hopital's rule again. We could use HR again, but what we just said up there is that that's not the best plan. Oops. That's usually not the best plan. I am going to want to simplify before I just apply it again, but simplify first. Okay, so then we're going to go down here and we can see then when I'm doing my simplification, I'm going to think of this as the limit as x approaches infinity of 1 over x, I'm going to pull that 1 over x out front, times 1 over 1/3 x to the negative 2/3. So this right here, remember, division by a fraction is the same thing as multiplication by the reciprocal. So this is 3 over x times x to the negative 2/3. I forgot my limit sign, my bad. The limit as x approaches infinity of 3 over x times x to the negative 2/3. But we know that x to the a times x to the b is equal to x to the a plus b. So this is the limit as x approaches infinity of 3 over x to the 1/3. And here I just used x to the a times x to the b is equal to x to the a plus b. So x times x to the negative 2/3 is x to the 1 minus 2/3. So now when I plug in, I don't get 0 over 0 anymore. In fact, I just get 0 because I get that division by infinity. And so I avoided doing L'Hopital's rule 2 times because I simplified first. Okay, let's do one more example of L'Hopital's rule multiple times. All right, so here I have the limit as x approaches negative infinity of e to the negative 2x plus 3 over x squared minus 2x plus 1. So the first thing I want to do is plug in. So I'm going to do this down here. I have e to the negative infinity plus 3. So that's e to the positive infinity plus 3. And we just saw up there with our graph that that's just infinity. So here I have infinity on top, and clearly I have infinity on the bottom as well. So I can use L'Hopital's rule. So I'm going to write a little HR over my equal sign to show that I'm using L'Hopital's rule. The limit as x approaches negative infinity, up top I'm going to need a little chain rule. So I'm going to have e to the negative 2x times negative 2. And then I will have on the bottom 2x minus 2. So there is simplification that I could easily do here. I can factor out that negative 2 or that 2 on the bottom and cancel out the 2's. It's not 100% necessary in this problem because it doesn't really get rid of any x's or change the form of the problem at all. That said, I'm still going to do it just to really get us into the habit of making sure that we always simplify after we have taken L'Hopital's rule. So I'm actually going to write s on the top here. So I'll have the limit as x goes to negative infinity. That s is to show that I'm simplifying. And then I'll factor out a 2 here, and I'll have x minus 2. And those 2's cancel out. Like I said, if you miss that step, it's not a big deal. But if that had been an x that I could cancel out, it would be a big deal because that would change the form of our problem. So this is limit as x goes to negative infinity of e to the negative 2x over x minus 2. And we're still going to get infinity over infinity when we plug in here. So we're going to apply L'Hopital's rule again to get the limit as x goes to negative infinity, e to the negative 2x times negative 2 over 1. And now when I plug in again, did I forget my negative? I did, my bad. I just love forgetting negatives. So that means I'm going to have a negative out here as well. So when I plug in again, I'm going to get negative, and then that e to the negative 2x we said is a negative infinity, times negative 2, and that's going to give me a positive infinity as my final answer. So we used L'Hopital's rule 2 times, and we simplified in between. All right, that's all for this video. Bye, guys.